Okay, good morning everyone, and welcome to the thu-devito tutorial on geophysical modeling. And as you can see, we called this tutorial from zero to devito. So we're going to take you through the basics of how to use devito and set up some basic seismic problems and overview some of the main sort of features for developing more advanced features with devito. Here we have our GitHub page for the workshop material at thu-devito Codes Transform 2020. And if you scroll down to the README here, there's some information about the tutorial. So an overview of the material we'll cover today. We'll start off with an introduction to the DSL, so how to express PDEs using devito. And then we'll have an introduction to devito operators. So this is where devito takes the equations and conditions and problems you've set up and turns them into optimized C code. Then we'll take a look at how we can build some basic wave propagators with devito. And finally, we'll finish off by looking at how we can express some more advanced boundary conditions using various features of devito. So if we scroll down here, so if you don't have devito installed on your system, but you want to run through and play around with material, we've set up this Azure VM with a Jupyter Hub, which you can log into to get access to all the material. So I'll quickly take you through the logging in process just to show how this works. So if we click on the link in the README, you'll be taken to the screen. You'll be able to sign in then to the hub with your GitHub credentials. Then this will take you into the Jupyter Hub. If it's your first login, you won't see any folders there currently. What you need to download the material is click on New, Terminal. So launch your terminal and set everything up. After that's done, if you navigate back to your other tab, you'll see then that you have the folders devito and Transform 2020. Then if you click on the Transform 2020 material folder, workshop notebooks, and then all the notebooks we'll cover today are located there. And I'll start off with the introduction DSL notebook. So to start off, we'll introduce the devito DSL, and to use devito, we need to get familiar with some of the main devito objects. So for convenience in the notebook, we'll import everything from devito. And the first object we'll introduce is the grid. So when we're defining any functions and so on, to define these functions, we're going to need a computational grid. We can define devito grid in the following manner. So if we look in cell 2, we say grid is equal to grid, and we need to provide this object with a shape and an extent. So here you can see that our shape has contains 2 elements, and therefore we're defining a 2-dimensional grid. If we print the grid object, then we can see that this grid has an extent of 1 in each of the dimensions. As we said, it has a shape of 5 in the x direction, 6 in the y dimension, and because we didn't specify any names for the dimensions, our dimensions have been given the default dimensions x and y. So with a grid built, we can now start looking at how to define a function in devito. So, and with all devito objects, if we want to look at the documentation for the object, we can type name of object underscore underscore doc underscore underscore to get the doc string for that particular object. And then that will print out all the parameters which we can pass to the object. If you look through various doc strings, you'll see that some of the parameters are required, others are optional and have default values. And you can take a look through that at your own pace. I'll mention that these notebooks, there's a lot of additional words in the notebooks we've provided in these tutorials. So these notebooks are designed to be sort of read in a standalone fashion, and therefore when I'm going through the notebooks in the workshop today, there'll be I'll just be pointing out the main sort of the main aspects I want to focus on within these notebooks. Okay, so now that we've defined our grid, we can define a function on this grid. So if we say f is equal to function name f, and we pass this function the grid that we have just created above, we print f, we can see now we've got a function of x and y. Our function's inherited the grid we've passed it to it, and therefore it knows that it's going to be a two-dimensional function of the dimensions of grid. The next important property to look at of f is the data property. So if we print out f.data, this is where all the data associated with each point on our computational grid is contained. And above, we defined our grid to be of shape 5, 6. There is it there. And therefore, we can see that our array is of shape 5 in the x direction and 6 in the y direction. Another function or another thu-devito function available is the time function. And so if we define our function g to be a time function, and again we just give it a name and pass it the grid, and we print that, you can see that on top of the two-dimensional grid, we now have a time dimension added. And if we look at g.shape, when we looked at, if we looked at f.data.shape, we would see someone had a shape of 5 and 6. But now with g.shape, you can see it's been allocated a size of 2 in the time dimension, and then 5 in the x direction, 6 in the y dimension. And that is because it's got a default time order of 1. We'll come to exactly why this shape of 2 has been allocated shortly. So the next thing, when we're forming any partial differential equation, we know we're going to want to take derivatives of these functions. And so if we want to take derivatives of these symbolic functions, there are various shorthands available in the thu-devito DSL. So let's start off by, so if we look at this table here, we can see if we want to take the right derivative, we can type f.dxr to get this discretization. If we want to take the left derivative, we can type f.dxl, get this left discretization. And of course, we can take these derivatives with respect to time as well. So if we look at g.dt and print that out, then we get a symbolic representation of the partial derivative of g with respect to time. And if we want to look at the actual finite difference discretization that it's producing, we can type g.dt and evaluate. And then we see that by default, we're getting the right discretization of that derivative in time. So there also, we have some shorthands for representing other sort of other forms of G, which we're going to frequently want to use in partial differential operators. So useful shorthand is G dot forward, which is giving us our function G at the next time step, and G dot backward, which gives us our function G at the previous time step. And of course, we can take the derivatives of any of these shorthands. So G dot forward dt will then be giving us the derivative at the next point in time with respect to time of G. And of course, we can do these. We can take these derivatives in space also. So now we've introduced the grid and functions and time functions. Let's take a look at how we can build a simple operator to solve a CFD problem. So here we'll take the linear convection equation. So our equation we're going to solve is that the partial derivative with respect to t plus some constant c times the derivative with respect to the partial derivative of our field u with respect to dx, and c times the partial derivative of our field u with respect to y is equal to 0. So this is our equation, and we're going to start off with some initial distribution and then convect that in time. So here we're gonna create the grid. We're gonna run our simulation for 100 time steps. Use a time step of this value here, and we'll set our constant c, appearing in the above equation, to be equal to 1. Then we define our computational grid, which is going to have 81 grid points in the x and in the y directions, and the extent of our grid will be 2 in the x direction and 2 in the y direction. Then we will define our field u to be a time function, hold u, and we will pass it the grid we have just created above. Now we're going to set the initial conditions. And so if we set our field u dot theta at the 0th time step to be equal to this function here, and we apply this in its smooth, what we get is this shape here. So this is our initial field, and then we are going to create a thu-devito operator to solve the evolution of that field in time according to our partial differential equation here. So in order to do this, we define the equation using the thu-devito symbolic language. So we'll call our equation EQ, and we use the thu-devito equation object and say that this equation is equal to u dot dt plus c times u dot dxl plus c times u dot dyl. And here we have not provided a right-hand side to the equation, and therefore it is by default set to 0. So an equivalent expression, if we wanted to set the right-hand side of the equation, would just be that thing there. And then if we print that equation out, we can see that we have a representation as with our mathematics written above. Of course, we set c to 1, and hence that has been simplified and removed from this equation. So now we need to arrange this equation to form our finite difference tensor. We need to, using our finite difference discretization, we need to rearrange the equation such that we have u dot forward, so u at the next point in time on the left-hand side of the equation. One way we can do this, if we say stencil is equal to solve our equation for u dot forward, and then we can say that our update is equal to the field u at the next time step on the left-hand side, and we can place the stencil on the right-hand side. Then, if we print out our update equation, we get the finite difference representation that we have defined. And so here we can see that we have u at the next point in time is equal to this stencil here, which is the scheme as we would expect. With our finite difference scheme created, we can now pass this to the thu-devito operator. So if we use the command op equals to operator and pass it our update equation, then this is where the thu-devito compiler will take our finite difference stencil and convert it into an executable C code. And to execute that code, we just call the operator again, telling it how long we want to run for, how many time steps we want to run for, and the DT we wish to use. And then that will execute the operator. So, and if we run that and then plot the field at the end of the simulation, we can see then that, as expected, our initial distribution is being convected through the domain. And we can also see the effects here of numerical dispersion. And so this operator here is where the real power of thu-devito lies. So this is where all the setup of our problem is analyzed, and then the C code, which depending on how everything is being set up, is generated for for the specific architecture on which you're working with. And if we actually want to look at the C code that this operator is generating, we can use the command print op.ccode and look through, take a look through that to see the exact scheme which is being implemented. So before we go on, a couple of things just to point out. So when we set up our functions above here, when we set our time function u, we weren't telling it, we weren't telling the time function what order of finite difference discretizations we wish to use. Hence, the default orders were being used, which are a time order and space order of 1. So later on, we'll see how we can change them to create different discretizations in space and time. So then to finish off this notebook, we'll look at how you can compose different stencils using the DeVito DSL. So here now, we're going to define a new time function u. We'll pass it again our grid, and this time we're passing it a space order parameter which we set to be 2, which is then telling us, telling DeVito that we want now that our scheme to be second order accurate in space. And then there are a range of shorthands available. Another one here is the dx2, which is just the second order derivative of u with respect to x. And if we evaluate that, we can see that we're getting a second order accurate scheme in space for the second order derivative of u with respect to x. And we can increase this space order arbitrarily to create schemes which are more accurate in space. So if we switch our space order to 4 and take the second order derivative with respect to x then, and look at the finite difference stencil that produces, we can see then we have automatically got a more accurate discretization. And above, we were just looking at, we just defined a 2D grid, but of course we can easily define a grid in 3 dimensions just by adding an additional value to the shape and extent arrays. So now if we define our grid 3D to have a shape of 5 in the x direction, 6 in the y direction, and 7 in the z dimension, and an extent of 1 in each of those dimensions. Then if we define a time function u on this grid, so now we pass it grid 3D, and we can say that we want this to be second order accurate in space. Now we have, print that function, we have our function u of t, x, y, and z. And we can redefine our function u as we like. So now, if we want to make it 12th order accurate in space, we just ramp our space order up to 12. And another convenient shorthand which is available is u dot Laplace. This is, we'll take the Laplacian of our function u for however many dimensions we have provided with. So for our u defined on a 3-dimensional grid, if we take the Laplacian, we would then get in the second order derivative of our function u with respect to each of the grid dimensions. So equivalently, the same expression could be generated explicitly via u dot dx2 plus u dot dy2 plus u dot dz2. And we can see the mathematics being printed out is equivalent. So above, we have just been generating derivatives of single functions, but these various shorthands for the derivatives can be applied to composites of functions. So we'll start if we define a differential operator v, the v dot dt2 plus u dot Laplace, and we print that out. We can see we're getting a Laplacian operator on u plus the second order derivative in time of our function v. Just to note that when defining these functions, we passed it our original grid, which was the two-dimensional grid of shape 5 and 6 defined previously. So with this equation, or with this expression created, we can further take the derivative of this expression if we like. So if we want to then differentiate our expression again with respect to x twice, then print that, we see we get this composite expression here then. And of course, if we want to view the actual finite difference discretization that produces, we can just add on the evaluate method, and then the discretization will be printed out in its full glory. And of course, we can do this. We can do this to any expression we want and create sort of arbitrarily complex finite difference stencils using the composite nature of the DSL. Okay, so what I should have mentioned at the start of the talk. So at the end of each notebook, we will take a short break. So let's stop here for 2 minutes, and then we will I'll get back and start on the second notebook, where we will go through some more of the details of the thu-devito operator in about 2 minutes' time. Okay, so welcome back. So, seen in the Slack channel, there's been a few questions about connecting to the Jupyter Hub to get access to these notebooks. So I did a very quick demonstration of that at the start, but I will now do a slightly more detailed one. So to get access to the Jupyter Hub with all the tutorial materials pre-set up, if you go to this web page here, github.com, thu-devito codes transform 2020, and then navigate down to the README. In the workshop prerequisites section, is to access the workshop material section of the README. And if you're using the Azure VM method to get access to the material, a link is provided. So if we click on this link, we'll open it in a new tab. You will then be taken to a page to log in with your GitHub credentials. I am already logged in, and therefore it's taking me straight to the Jupyter Hub. But on the sign-in page, if you put in your GitHub credentials and then sign in, you will be taken to the Jupyter Hub, which upon first login will have no folders present. On that blank Jupyter Hub, if you click New and then Terminal, a terminal will open in the next tab, and that will set up all the material required for this tutorial on the Jupyter Hub. So it will clone thu-devito and install all the requirements for that, and also it will clone the Transform 2020 repository with all of today's material. After that has completed, if you go back to the previous tab, you will now see that you have two folders present, thu-devito and Transform 2020. If we navigate into the Transform 2020 folder, there we can see all the workshop material is there. In workshop notebooks, there you'll see the 4 notebooks on which today's material is based are all there. And if we click on one of these notebooks, so now we're going to look at the Introduction to Operators notebook. You can just open that up, and then everything in this notebook should run. Okay, so that should cover everything with respect to our Jupyter Hub for now. And when we need to do additional things with Jupyter Hub, we'll come back to that later. Okay, so in the previous notebook, we had a brief introduction to some of the most important thu-devito objects, which were the grid, the function objects, where we looked at the function and time function, and also we looked at quickly how we can use the operator. So now we will look in more detail at the operator object, and in particular we will look at the operator.apply method and the operator.arguments method. We'll also describe in more detail the data objects which is associated with functions, and talk about how these data objects are updated during the execution of thu-devito operators. So now the thu-devito objects we're going to need are grid, time function, equation, and operator. So these are the four of the objects we saw in the previous notebook. Previously, we just imported all the thu-devito objects using the import star expression, but now we'll import the individual operators here. As we did previously, we will now define a grid. Our grid will be two-dimensional and have a shape of 4 and 4. Hence, we'll have 4 grid points in each of the x and y directions. We're now going to define a time function. We'll call it u. We'll pass it the grid we have just created, and we will also additionally pass now the parameter save equals to 3. And if we, which I'll explain in more detail shortly. Now, if we execute, or if we create an operator, which is the equation u dot forward. So as we saw in the previous notebook on the DSL, we saw the shortcut u dot forward was a representation for u at t plus dt. So our time function u at the next time step, and we'll set that to be equal to u plus 1. Hence, at every iteration, now we are simply adding 1 to the data of our function u. So if we then execute the operator using op.apply, and then we can look at the results of that operation. So just some details about our problem. So if we look at u.dimensions, as expected, we set up a time function on a two-dimensional grid, and hence we have the problem dimensions are time, x, and y. If we look at the shape, we have our grid shape 3, 3, and you can see in the time dimension we have a shape of 3. And in this case, the shape of 3 is due to setting the save parameter to be equal to 3. And hence, if we set this parameter to 5 or whichever number we like, our u dot shape will just have that equivalent number in the equivalent size, I should say, in the time dimension. So if we look then at u.data, you can see we have these 3 shapes, or we have these 3 entries of 4 by 4 arrays. And in our operator, we were adding 1 at each iteration. And hence, when we look at the results, we can see here's our initial condition. So when we initialized our function, it had 0 data, since we didn't specify anything. And then after the first iteration, we have just simply added 1 to the data, and then after the next iteration, we have added another 1. And I think we have an example where we use a different save parameter just below. But of course, if we set this to be save equals to 5, by default, the op.apply would fill that array running or executing the operator we have defined just above. Now, if we look at op.arguments, we can see that we can then look at the various arguments which are associated with this operator, and therefore which we can, if we like, we can pass to the operator when we execute it. To explain these then, so we see time m. This is the first time step which will be executed. So time underscore m represents the first time step which our operator is going to execute. Time size represents the size of the time dimension of our object. And time m represents the final time step, which will be executed. Time underscore big M represents the final time step, which will be executed. X underscore M represents the first node in the X dimension, which we want to execute on. X size, the size of the problem in the X dimension, and X underscore M represents the final node in the X dimension which we wish to operate on. So this problem is on a 4x4 grid, hence 4 nodes in the X direction which are labeled 0, 1, 2, and 3. And that's why here, by default, we have that the entire grid or the entire X dimension is included in the default setup, and the same here for the Y dimension. And now we'll see how we can play around with these parameters a bit by passing them to the operator in order to execute slightly different functions. So if we look at if we now reset our data to be equal to 0, and if we then run our operator, so we can see here that this time we're passing the parameters x underscore m equals to 2, y underscore m equals to 2, and time underscore big M equals to 0. So what this is telling the operator is that we want to now start the iteration at the third node, so x in the X dimension and in the Y dimension. And as I said, time underscore M was the final time step we wish to operate. So this is saying that the final time step we want to operate, we want to execute, is the first time step. Hence, this then will only run for one time step on the lower quadrant of the grid. So we execute that. So previously, without passing any arguments, we saw that this operator, as we expected, just added 1 to the entire grid at each time step. But now, with these arguments passed, if we go down and look at the result, we can see that we have our initial condition, and then owing to the parameters we've passed, 1 has been added to the lower quadrant of the grid at the first time step, and we set Tm equals to 0, and that was telling the operator that we only want to run for one time step, and hence nothing is happening for the third. That is in the third slot because no time step was executed then. Of course, if we set this to be equal to 1, I'll probably need to just run through some of the cells above. Okay, so if we run that now, setting Tm equals to run, then of course we will add on the next iteration, and hence fill up the 2's there. if we say wanted to run for use the entire y dimension, then sorry, the entire x dimension, we can just flip that to be our x underscore little m to be equal to 0, run it, and then we can say that in this case now the entire x dimension has been filled for both the time steps. Okay, and as I mentioned, so now if we change our save parameter and say we want to set save equals to 5, and we look at that, then and execute this operator. So just a note here that so if we create a new time function u2 with this new save parameter 5, and then we want to reuse our old operator, we can just say op.apply, and we can pass the parameter u equals to u2. So when we created our original operator, we created it with the function u, and hence when we looked we created it with the function u, but we can, if we want to use a different function instead of u, but we don't want to remake the operator, we can just pass that function to the operator, and it will then replace the original u with our new u and execute everything accordingly. Okay, so if we look at then the output of u.data, we can see that it is now executed for the 4 time steps. So we set save equals to 5, hence we can run for 4 time steps plus our initial condition, and we get this result. Okay, so now we will define a time function v. We'll pass it the original grid, and again we'll make the simple operator. Now we'll call operator 2, which will just again add 1 to our time function v at each iteration, and we will then execute this operator setting time m equals, or time underscore big M equals to 4. Okay, so this is saying we want to execute, or we want to run for, so this is saying that the final time step we wish to execute is the 4th, and so we're gonna run for we'll added 5 data elements. So notice when we defined our function, we did not specify a save parameter here, and hence I'll just insert the cell below. If we look at v.shape, we'll see that this function has a shape of 2 in the time dimension. This is because the default space order of the function is 1, and hence the minimum the minimum shape required to execute any operator with this function is 2 in the time dimension. And so when we then execute this operator, in order to be memory efficient, thu-devito will automatically overwrite the appropriate the appropriate time slot to store, well, to execute the operator. So, for example, if we set this to be 0, and let me just, before we execute, let's just 0 the data. So if we run this thing, so as expected, we have now executed for one time step. Just remove that, and we have our initial condition plus the data at t equals to 1. Now, if we set t equals to what? T underscore again equals to 1, so that we're executing for 2 time steps, and we rerun this. You can see now that we have our first time step here, but our first slot in the time dimension has then been overwritten with data from the next time step, and so on. And so this, and then that process will repeat. Just checking if I have an example with a higher. No, I don't. So let me just show that now. So, and if we specify a higher space order, sorry, a higher time order. So if, for example, we wanted our function to be second order accurate in time, for any discretization, which is going to respect that accuracy, we're going to need in u dot forward is going to rely on u and also u dot backward there, and hence we're going to need the minimum size in the time dimension needed to represent such a scheme is going to be 3, and hence when we define that, if we look at u dot shape now, you can see then that now our time dimension has been allocated a size of 3, and so on when we run that. Oh yeah, so that is now updated, and now we are showing the size of 3 in the time dimension. And there is also then the, so we can see when we run this operator above, we set it to be, we set summary to be equal to the application of this operator. And so if we look at what this summary variable contains then, so if we print summary, this then gives us a performance summary of the execution of the operator, telling us how long it took and giving them various performance metrics. We didn't set up anything specific to tell the Vito to track the various performance metrics before executing this operator, and hence it's only giving us the time taken to execute the operator. If you want to get additional information such as the G flops, G points, and so on, there are additional profiling options which can be set, which are explained there. So here we import the configuration object, And if we set configuration profiling to be advanced, we create this operator, u.forward to be equal to u squared plus 1, and we run op.apply, and then we look at the performance summary of this operation. We can see then that owing to the advanced setting, additional performance metrics are now being tracked, and we are also being told the G-flops, the 2 points of that operator application, and so on. And there is, I won't go through this now, but there's some more details on how the performance summary can be used and which metrics can be obtained. Okay, so now we have gone over some of the, we've gone over the basic objects which are needed to construct various thu-devito objects, thu-devito operators, and also gone over some of the details of how to use the operator and how exactly thu-devito stores the data associated with functions. And so we have this little exercise where we're going to compare a thu-devito simulation against an exact solution of the 1D wave equation. So our problem is as follows. We have the 1D wave equation in a domain of length L equals 10 in the x direction. We have 0 Dirichlet conditions at each of the boundaries on the side, a 0 velocity condition for the inlet at time equals to 0, and our wave is going to be 0 between x 0 and less than 4, 1 between x is equal to 4 and 6, and 0 then again for between x equals 6 and 10. And so our initial condition looks like the following wave. So here are then some details to get you about how one can go about setting up an operator to compute the evolution of this wave in thu-devito. And so what we'll do now is we'll take a 10-minute break, and if you'd like, please sort of fiddle around and try and complete the code given to you during the break. And when we come back, I will quickly sort of go over how one can, or go over the bits of code needed to complete this propagator, and also then explain some of the parameters which can be tweaked to create better solutions. Okay, so we will reconvene in 10 minutes time.
Okay, welcome back. So just prior to the break, we started looking at a little exercise of how to create a DeVito operator to solve a simple 1D wave propagation problem. And there is a ready-made solution to this problem on in the workshop material, which you can find on the Jupyter Hub. So if we navigate to the Transform 2020 folder, looks like my connection to the hub has actually gone down. So let's launch the server again. So there in the Transform 2020 directory, if we navigate to additional material, and then there's the notebook nb2 underscore exercise. And if we open that notebook, this has a already made solution to the problem. So just to recap quickly what the problem is, solving the 1D wave equation in a domain of size 10. We have Dirichlet boundary conditions on each of the edges of the domain. The initial velocity of the wave is 0, and we have the initial condition given here, and here's then a plot of our initial wave field. So let's just zoom in on this. Just below there, I've written the exact solution to this problem, which we can write in terms of a Fourier series. Which is given here. And so to start, we've got a little bit of code where we define our domain and some parameters we need. So we've defined L, the length of our domain, to be 10. N here is the number of terms we're going to use in our Fourier series. L, the number of grid points we want in our domain, and we're going to set our constant C appearing in the wave equation to be 1. So first of all, if we make a discretization of that domain using linspace, and we're going to define our function u underscore e, which is just a function to compute the exact solution. So if we want to plot that exact solution using the parameters we've written above, we just get to plot our initial wave field. So now we will implement that in DeVito. So to start off, we're solving a second order equation in space and time. So the minimum space orders we can use are going to be 2 in each of those dimensions, which we've specified here. Later on, we'll start playing around with this parameter to see how this affects the accuracy of the solution. We'll start off with a space order of 2. Now we will import the appropriate DeVito objects. Here we're going to need the DeVito grid, time function, equation, solve, and operator objects. So let's create our computational grid. So we've defined L and little l and big L above. So we'll use them to define our grid. And we're going to grab here grid.stepIndIn. And this is the step-in dimension of the problem. So in this case, the time dimension, which is going to be used in any equation we form using this grid. So now let's define our wave field. Of course, is going to be a time function. We'll call it u, pass it our grid, and set the time order and space order to be the parameters we have defined there just above. So now we're going to work out what dx is. Looking at the code, I can't remember exactly why this is needed, but anyway, or I think it's maybe so you could use this to calculate the CFL number, but anyway, we'll set our critical time step dt here in this case. So dt needs to be for stability needs to be less than 0.42 times dx over c, and here to get a nice number, and so that after a nice rounded number of time steps the wave should return to its initial position, we'll set dt here to be 0.004. So now we can define our equation and the boundary conditions. So our partial differential equation is just the wave equation, so 1 over c squared times the second derivative of u with respect to t minus the second order derivative of u with respect to x. And if we want to form then our finite difference stencil, we're going to say that u forward is equal to solve of our PD with respect to u forward. And hence, this will give us u forward equals to the appropriate discretization. So now, during the specification of the problem, we said that we have 0 Dirichlet boundary conditions on each of the edges of the domain. So to represent these in DeVito, we can just we can just specify 2 new equations which enforce that these conditions must be true at those particular grid points. So this is a very simple boundary condition, and hence we can just say BC equals to equation. So U at T underscore S, which is our step in dimension, we just grabbed there. And the grid point is 0, and we want that to be 0. And equivalently for the condition on the right side of the domain, we're going to say that U, so just to emphasize that we've got T underscore S plus 1 here. So we're just saying there that at the next time step, we always want this condition to be 0. And then at the right grid point, so the shorthand using the -1 there, we could equivalently, I think we had 1,000 points, right? In the yes, we had a grid size of 1,001. So equivalently, we could just replace that with a 1,000, but we're using then the shorthand -1 here to get the endpoint, and we're also setting that to be 0. Another important thing to mention here is that now our scheme relies on U forward, U, and U backward, because we have a second order discretization in time. And hence we need to be a little bit careful with how we're going to set up this and push it through the DeVito operator. So generally, when we're solving one of these problems, we're going to need to use some approximation to compute the wave field at the first time step. But here, since we have the exact solution, we will just use that to compute what our wave field should look like at the first time step. So that's what we're going to do here. So we have u0, where we're just calling our exact solution function at t equals 0, and at the first time step, so at time dt, we'll also set the field u1 to be equal to that. Then we can use these two NumPy arrays to initialize our data. So then we set our whale field u.data at 0 to be equal to u0, and u.data at the first time step we set to be equal to u1. And now we can create our thu-devito operator. We'll pass it our equation, and we can just simply add on the boundary condition. So this BC, and then they will be included in the operator. So now we want to execute the operator, and at so after 5,000 time steps, the wave should return to its initial condition. And so that's why we set t underscore big M to be equal to 4999. So the 4999 will be the last time step which is executed, hence taking us on to the 5,000th iteration. Set our dt, and also importantly here we've set time underscore m, a little m, to be equal to 1, because now we have pre-populated the first and second elements of the time array. And so since we've already essentially computed the first time step analytically, we'll be starting our simulation at time underscore m equals 1. Okay, then we can run that forward in time and plot the results. And so that, as expected, for a problem like this, our wave is sort of returned to the initial condition or the initial position, but there's been a lot of numerical dispersion, and hence we get this wiggly result. And just to say, so here, so the if we look at the okay, so now if we want to play around with this to try and get a more accurate solution, one easy thing we can do is just up the space order. So let's just set that to be 12. I'll need to run through the notebook just to make sure everything is initialized. And now let's plot that result. And we can see we've upped the space order, and we've still got we've still got quite a bit of numerical dispersion there, but the solution has then improved. And of course, there are various things which you can play around with to improve the solution further. We could, of course, increase the time order of the discretization. So that will involve a little bit more work, so I won't go through that now. So if you wanted to use a time order equals to 4, say, then we just need to pre-populate a few more of our initial conditions using the exact solution and start the thu-devito operator at the appropriate time, and so on. Okay, so there's an implementation of a simple 1D operator. And now in the next notebook, so if we now, I should just open it from, here. So if we look at O3 Propagators acoustic and open that notebook. In this notebook now, we're going to go through the implementation of a 2D acoustic propagator in DeVito, where we're going to be constructing an operator akin to the type of forward model you would use within a seismic inversion problem. And so in order to do this, we're going to introduce the model class, which is a set of wrappers we've implemented in DeVito just to make the implementation of basic seismic propagators more convenient, which I'll explain a bit about soon. And the important new thing we're going to cover here, so we've already essentially seen how you can implement a wave equation in DeVito, but of course in a seismic problem, the components we're missing for doing that are sources and receivers. And these are sort of a set of sparse operations, which DeVito can handle. So we'll talk about we'll talk about them during this tutorial, and we'll use these components then to build a basic forward propagator. Okay, so the modeling workflow, the sort of what we're thinking about is a situation such as the following. So we have a seismic source from which we're going to emit our waves. They are going to propagate through some domain, and then the reflections are going to be picked up by a set of hydrophones. So these will be our receivers. And then the equations we're dealing with, written down here. So we have the acoustic wave equation, where now we're setting m to be the squared slowness. The setup will be in 2 dimensions. So on the right-hand side of our wave equation here, we have our source term. Our initial condition is that there's going to be no waves in the domain, and also the velocity field will be equal to 0 at time 0. Okay, so we're dealing with a finite domain, and so the addition we need in order to set up a propagation problem is some boundary condition. So in the next tutorial, we'll go through a more sophisticated boundary condition. But in this tutorial, we'll use a simple absorbing boundary layer where we just have some parameter eta times the first derivative of the velocity of the wave field with respect to time. And this will be our absorbing term. Eta is a parameter then which is 0 within the main computational domain, and then within our defined sponge region, this will ramp up. And the ramp up could be linear or exponential. Here we'll just use in terms of the basic model implementation, we'll just be using a simple linear profile for that. So now a lot of the setup is going to be similar to what we have seen already. So on top of the normal suspects of grid, function, equation, and so on that we're going to need to import from DeVito, we're also going to import examples.seismic. So this is the set of wrappers I mentioned above. And from that, we're going to import your model and this convenient plotting function, plot velocity. And so model is the important new input we are looking at here, and I'll explain more about exactly what this model class is doing as we go on. Okay, so first we define the shape of our computational domain. the space in, and the origin. So when we defined grids previously, we were passing shape and extent. But if you look at the docstring of the grid object, you can see there are various parameters you can pass to initialize that particular object. So if we don't want to pass extent, for example, we can pass shape and space in, and of course then extent is worked out automatically. So if we call our model class, we should say before we move on, let's define our velocity profile. So here we're defining an empty numpy array with dimensions shape, and we're setting that so that in the upper part of that array where we have a velocity of 1.5, and in the lower part we have a velocity of 2.5. So if we look at a quick plot of our velocity model, we just have this simple sort of two velocity profile. It's a two-layer model pictured there. So if we call this model class, so we're going to set VP equals to V, give it an origin, shape, space in, space order. So this is just the same as the space order we've seen before. So any functions which are set up are going to utilize the space order. And NBL. So this is an important new parameter, and this is setting the number of boundary conditions. The number of grid points in our boundary layer. And then we can also specify the type of boundary condition which we're going to use, and we're going to use this simple damping boundary condition I mentioned above. So again, this is just saying that our grid now, we're going to surround it with an additional 10 points on each dimension, and within those 10 points, our sponge layer will be initiated. And so what model is going to do then, it's going to set up our grid and add on this sponge layer. And then we'll be able to use various properties of our model then when we create our PD for solving the propagation problem. Okay, so now we will set up our time dimension. So we'll specify our T0. We'll start the simulation at 0. We'll run the simulation for 1000 milliseconds. So now, since we've set up this model class, this basic model is, we're telling it we're setting up a model for the acoustic propagation problem. And hence, based on knowing that, we have this model property model.critical dt. And this is going to compute the critical dt required for making our particular simulation stable. And then with that defined, we can define our time range using this time axis property. This time axis object, which is again imported from examples.seismic, and give it our T0, Tn, and our time step. So what this is going to do then is create an array containing all the points in time at which the wave field is going to be evaluated. And we're doing this is because we need to specify the source strength at our, we're going to need to specify source strengths at our particular source locations at these at the required times. So if we look at the, and again, as I mentioned, for any of our objects, if we want to look at the doc string, we can just use this command here. And then printing that out explains the usage of this particular object. Okay, so with that object created, we're now going to define our sources and receivers. The sources and receivers are wrappers, or in the seismic examples, are wrappers for the thu-devito sparse function capability. So sparse functions are another thu-devito object, which we don't have time in this tutorial to go into the details of, but basically they are objects, they're functions which are not on the actual computational grid. So the wrappers we've implemented here, you can of course implement these objects yourselves using sparse functions, but for the convenience of this tutorial, we'll just use these sort of preset sort of objects to set up the data in the sparse functions that we require. So if we set the peak frequency of our source to be 10 Hertz, and we'll set up then a Ricker source. So we'll say SRC is equal to Ricker source, give it a name, give it a grid. So when we created our model, that, as I mentioned, that created the computational grid, which we can access now through model.grid. Pass it the frequency. Here we're telling it how many sources we want to set up. So here we're just going to use a single source. And in order to set up the data associated with the source, we need to pass the time range. So it knows at what values in time that the value of the source is going to be needed. So after that's done, we can set the source coordinates. Here in this array, if we look at source.coordinates.data, the first entry relates to the receiver number, to the source number. So here we have only one source, and hence the only valid entry to this is 0. And then the second entry is the coordinates or the dimension of the coordinate for that particular source. So the 0 here indicates the x dimension, or the x position of that source, which here we set to be the middle of the computational grid. And then 1 indicates, or 1 grabs the y coordinate of the 0th source. And here we're going to set that to be at a depth of 20 meters. And if we want to look at the signal associated with our source, we say src.show. And then we plot then the source signal, which is given by the equation for the Ricker source defined above. So as a brief summary, what this is doing is it's creating a sparse function, and based on the equation above for the Ricker source, it's automatically populating the data or the value of that source at these set positions throughout time um, for this source. Now we've set up our source, we also need to set up some receivers. So a receiver is just, if we imports from examples.seismic receiver. So this is just another convenient wrapper for the time, for the DeVito sparse time functions, where we place a point. Well, we place these receivers at certain points throughout the computational domain, and then whichever field we want, we can get then the DeVito to automatically interpolate any field we're evaluating onto the receiver. So here we'll be specifying sort of what we want to pick up shortly. So we're just going to be picking up, based on the wrapper, we're just going to be picking up the wave field. So we specify the coordinates of our receivers. So here now we're specifying 101 receivers, and we're going to set them evenly spaced in the x direction, all at a depth of 20 meters. So if we plot then our configuration, so this is our model setup pictured here. So the green dots represent our array of receivers. I think we're plotting 1 in 4 of them there, so they're much more densely placed than they're actually being plotted here. We have a single source, illustrated by the red dot, and our velocity model. We have a velocity of 1.5 kilometers per second in the upper layer, and then we have a lower layer split in the domain in two, with a velocity of 2.5 kilometers per second. So let's then look at the finite difference discretization we're going to use for this problem. I'll just go through this quickly. So we're going to use a second order scheme in time, and hence we have the discretization given here, and the spatial discretization for some general shape, for some sort of general space order, can be written as given here. And so we're already familiar with forming PDEs in DeVito. So we do this for this particular example in exactly the same way we did for the sort of previous example of the 1D propagation, the 1D propagator, but now we're passing it our two-dimensional grid, which we're going to grab for model. So here we define our wave field to be a time function. We pass it model.grid, set the time order and space order to both be 2. And the addition we are using here is we're in 2 dimensions, so we're using the shorthand u.Laplace. We're also, for our c, for our 1 over c squared, we're just using model.m. So when we pass the velocity of p waves to the model, then the model automatically calculates 1 over c squared, and hence we can just grab that straight from model. And I also mentioned we're going to add this absorbing term, and so we have this term model.damp times u.dt. And so here model.damp is going to be just a NumPy array, or so in this case it'll be a DeVito function. but it's essentially then like a NumPy array which spans our grid. So we specified our grid to be 101 points in each the X and Y direction. So with the absorbing layer, so when we defined model, we defined the number of boundary layers to be 10. Hence, the model grid which is created will have a shape of 121 by 121 because we've added on this these 10 points in each of the directions, in each of the dimensions. And then model.damp will be a field with 0 within the main domain of 101 by 101, and then will be ramping up, as I mentioned, within those 10 boundary layers. If we look at OPD, you can see that we have this equation here representing our mathematics. And then in the same way as we did previously, we can set up our finite difference stencil by saying that we want u.forward to be equal to the solution of the PD for u.forward. And if we look back at our discretization of the equations, so which we wrote up here. So on the original equations, we specified that the source term was Q, and hence when we do our manipulation and form our scheme, we can see that we need that Q within our discretization. We need that Q to be multiplied by dt squared over model.m. So here, this is our discretization. So when we go through the maths, we'll get u at the next time step is equal to this thing here, and we see that q ends up within in a bracket with this delta t squared over m. And hence, when we define our source term, then we're going to say source.inject. The field we want to inject into is u.forward, and the expression which we're injecting is our source term times dt squared over model.m, coming from this here. And then our receiver, as I mentioned, is just going to be an interpolation onto the receiver locations, and the field which we wish to interpolate is just u.forward. So we just want to interpolate our wave field onto the receivers. Then we can set up our thu-devito operator to solve this problem. So we say OP is equal to operator, pass it our stencil, and then in a similar way to how we added the boundary conditions in the previous 1D wave propagation example, we can just add our source and receiver terms in the same way, and as so. And here, because we're using a model which is creating a new grid, we need to specify this substitution, and that's model spacing.map. Okay, and then we can run. Now we can run this operator, and we want to run it throughout our. So we specified our time range object, and if we can run that then through, if we want to run it for the number of time steps -1 because we're starting from the 0. Set the dt to be equals to model.critical dt. Run through that. That will then perform the simulation, and if we wish to then plot the shot record with our receivers, we have another convenient wrapper function in examples.seismic. So from examples.seismic, if we import plot shot record, then execute the command plot shot record rec.data, give it our model, T0 and the Tn, then that will plot the shot record at our receivers. Okay, so then to finish off this notebook, before we move on to talking about DeVito subdomains and how to utilize them to set up sort of more sophisticated boundary conditions, we'll just talk a little bit about running DeVito with MPI. So DeVito is of course designed to be a high performance, will produce high performance C code, which we're going to want to run large scale production size problems with, and hence we're going to need to execute them on clusters in parallel. Now, an important sort of design philosophy of DeVito is that when the code you're executing on your laptop, when you move that to run on a HPC cluster, the actual DeVito code doesn't need to change. And therefore, all the MPI implementations are hidden under the hood. And so if we're running a program on our laptop, where we're just doing Python myprogram.py, which is executing various DeVito operators. If we now want to run that on a larger system, we don't need to change the code at all. All we need to do is when we're running that program, we need to, in a command line, type DeVito MPI equals 1, MPI run, then specify specify the MPI args, Python myprogram.py. Okay, so let's just go through an example of doing that on the Jupyter Hub. So if I might need to start up a new terminal here. So if I now launch my server, go to new terminal. Okay, so on the Jupyter Hub, when you launch a new terminal, you'll be automatically in the DeVito repository. So as I mentioned within the script here, so if we run the command pip install -r requirements optional .txt and run that for the user. So I've already run this previously, so it will go quick. If you're executing this freshly on your machines, it will take a little bit longer to build all the required packages. But once you've installed all the optional packages, then DeVito should be ready to work with MPI. So now if we navigate back to the transform repository and go into the additional materials directory, in there we can see we have this script, acoustic script.py. So first of all, let's just execute that in serial. So if we say Python acoustic script.py, so this script is essentially the Wave propagator, we just I've lost the, oh, here we go. So this script is basically this propagator, except with the plot in and of course all the words taken out. And if we run that in serial, we can see that we get the norm of the receiver data to be its value 370.04, etc. Now let's execute this using MPI. So we've not modified the script at all, but now we will turn on MPI by saying .devito MPI equals to 1. Then MPI run minus np2 Python acoustic script .py, and let's execute that. And so now, of course, because we're running on over two MPI processes, we're going to get double the terminal output. But you can see then that yeah, just add in those arguments. Same script has worked without any problems at all, and we're getting the same norm at the receiver data. Okay, so the final notebook of the session will be based on based on setting up some boundary conditions in .devito, and we will set up a more sophisticated boundary condition and then apply that to the acoustic operator we've just been looking at. But before we move on to that, we'll just take a 5-minute break. So we'll start back in 5 minutes. Welcome back, everyone. So in the final notebook of this tutorial, as I mentioned, we'll be looking at how to implement more sophisticated boundary conditions in DeVito. And for that, we will need the subdomain object. So we'll start by going through this object and then look at how we can add on some more sophisticated boundaries using subdomains to the acoustic propagator that we implemented in the previous notebook. And just a note, so the rest of the material is going to take about 30 minutes to get through. And once we've done that, if there is any interest, there will be a short Q&A session. So if there's any questions you have about DeVito, anything you would like me to address, please, within the next 30 minutes, mention those in the Slack channel. And then after I'm done with the material, we'll take a quick 1 minute break. And then we can come back and address any questions which have popped up or anything you would like to ask about DeVito. Okay, so let's get going. And as an introduction to subdomains, we'll start by creating a DeVito grid. We will define this grid to have a shape of 10 in 3 dimensions. Then we'll make our grid. And if we look at grid, the property, grid.subdomains, you'll see that we have these 2 subdomains, domain and interior, which have been created by default. And so these subdomains, these default subdomains, are used for internal DeVito reasons, and generally users don't need to concern themselves with them. But users may want to utilize this subdomain feature to create various to do various things themselves. So let's look at the properties of these subdomains. So if we look at grid.subdomain domain, we can see this subdomain has dimensions x, y, and z. And if we look at the shape, it is a shape of 10 in every dimension. So we can see that this subdomain is the actual full computational domain. If we look at grid.subdomains interior, we can see that this has now some different dimensions, this I0x and so on. And if we look at the shape of this subdomain, we can see that it has a shape of 8 in each dimension. So what in fact the subdomain is, it is the each dimension, the grid in each dimension, but excluding the boundary node. And that is, as I said, set up by default when you create a DeVito grid. So if we look at how we can construct such subdomains ourselves, we will first import the subdomain object from DeVito. And then if we define this class, which we'll call full domain, and we're going to say def define the dimensions of the subdomain, and we're going to say x, y, z equals the dimensions, and then we're going to say we're going to provide this dimension map, which is saying we want x to be the full x dimension, y to be the full y dimension, z to be the full z dimension, and then we can initialize this object by calling our subdomain something, which we'll just say full underscore domain, and equals to full domain to initialize our subdomain. Then when we create our grid, we can pass this subdomain's parameter. So now we'll pass it a tuple with the full domain subdomain. And if we look at then mygrid underscore domains, subdomains, we can see that this my domain subdomain has then been added to the set of subdomains, and this domain is of course going to be the same as domain in this case, but it's now a user defined subdomain instead of the default one. Okay, but there, when we were defining our subdomain, we were just setting the dimensions to be those of the full grid. Of course, we can specify these dimensions to be subsets of the full grid in order to pick out a certain part of the computational domain we want to operate on, for example. So if we want to then define our own subdomain to be like the interior domain, where we exclude the grid point at the end, or the end grid points of each dimension, then we could say class inner domain, give it a name, and then when we define our dimensions, we can say for each of our dimensions, middle dash 1 1 for the in dimensions. And so middle is one of the keywords implemented within DeVito for defining particular subdomains. So here, the form of this needs to be middle NM, where here the first number n, so the 1 here, is telling us how many points of the computational grid we want to exclude on the left side, and then of course the next number is telling us how many points of the computational grid we want to exclude on the right side of each dimension. There are two more keywords we can use, which we will look at examples of in a second, left and right. And for those, when we define d left n, we are just saying that we want the computational domain in that dimension to be the left n grid points. And if we use the keyword right, we are saying that we want the computational domain in that dimension to be the n right points. Okay, so we define this class inner domain, and if we initialize an object using that class, pass that to mygrid. So now we're passing the previously made full domain and now the inner domain. And if we look at mygrid dot subdomains inner dot shape, as expected, we are getting the shape 888. Because we are excluding our grid is 10 cubed, and we're excluding the points at the end, at the start and end of each dimension. So now let's look at how we can define some domains and utilize them within DeVito operators. So we'll first define a subdomain which we're going to call middle. As before, we will define our dimensions, but now here we'll use middle and say 3, 4, and in the x dimension, and in the y dimension we'll specify that to be middle 4, 3. So in the x dimension we're excluding 3 computational points on the left, 4 computational points on the right, and in the y dimension 4 and 3 respectively. So now if we import the DeVito objects needed to create an equation and an operator, we'll make our grid, passing it to subdomain middle, define a function on that grid, and now we'll define a DeVito equation where we, at each iteration, we're just going to add 1 to the function. And now, because we want this operation to occur only on a subdomain, we're going to pass an additional parameter to the equation, which is grid.subdomains middle. Then when we execute our equation, we can see that we have only updated this small section of the computational grid where we've excluded the points on either side as we specified when defining our subdomain above. And so similarly, we can define some subdimensions using the left and right keywords. So if we say here, we say we want the x dimension to be left, the 2 grid points on the left of the domain. We'll let our y dimension be the entire domain. And if we set up some right subdomain where we're letting the x dimension be the entire dimension and the y dimension to be the right 2 grid points of that dimension, then we can similarly create another equation and operator. So we'll create equations on each of these subdomains. So in the middle, we'll specify that we add 1. On our left subdomain, we'll specify that we add 2. And on the right subdomain, we'll specify that we add 3. And yet, just to point out again, when we've created our grid, we've passed these subdomains mid LD and RD as defined above. So if we create and run our operator, where we pass these 3 equations and then look at the result, we can see that as expected in the middle subdomain, which doesn't overlap with any subdomains, we've just added the 1. On our top subdomain, on our left subdomain, we have added 2. On our right subdomain, we've added 3. And on the overlap between those subdomains, we of course, both operations have been performed where we've added the 2 and the 3. So here's then was a little exercise where if we can say, okay, so we want this result. So how do we construct a DeVito operator from a zeroed data array to in one iteration go to this thing here by using subdomains? And on the Jupyter Hub, if we go to the transform, I need to reload my server. If you, in the transform 2020 directory, if you navigate to additional material and open up the NB4 exercise notebook, then there is a quick explanation of how to do this. So you can see here we have 4 distinct regions. Well, I think here is a copy and paste error. I'm sorry. So this, of course, should be a 0. So to do this, we'll define 4 subdomains, which we'll call top left, top right, bottom left, and bottom right. So for our top left domain, which we want to be this one region, we're going to define the subdomain so that it excludes 1 point on the left and 5 points on the right in each of the dimensions. Again, we'll use the middle keyword here. And then similarly, we can define each of the other subdomains appropriately to only iterate on our small section of the code. And then we initialize those subdomains. When we form our grid, we pass the 4 subdomains we've initialized to it, create our function, create our equations, pass them to an operator and execute. And let me just run through this live, making sure it all works. And then, yeah, when we look at our f.data, having defined those subdomains, we get the appropriate result. So just to point out, another way we could have done this would have been not incrementing, defining some overlap between the subdomains, and then incrementing by 1 on each domain appropriately. And then if we have we could have just had one equation, f plus 1, and then defining the overlaps between the domains appropriately, we could have got this this result as well. So of course, there's just pointing out that there are many different methods through using subdomains from which we could get to this particular result here. This is an illustration of one of them. But yeah, the idea behind that was just to give you something to play around with to get you used to the implementation of subdomains. So now that we've got the idea of subdomains and how we can use them to pick out certain regions of our computational domain and define equations which are executed only on those particular subdomains, we can then utilize that feature to try and implement some boundary conditions. So here we'll go through an implementation of a PML layer, which will add to then the acoustic wave propagation example. Just to point out, there's a lot of additional mathematics within this section of the tutorial, which I'm not going to go through in detail. The important, I think, the paper from which this implementation is based is referenced here. So for the full details of the mathematics, please look at that link. But what I'll focus on here is how we use thu-devito along with equations to implement that setup described in that reference. So our configuration will be as follows. We'll have our main propagation, main domain. On the top, we'll have a free surface, and then on each of the sides, we will specify 3 subdomains where the PMLs will be based. I should note that we could have, there are various ways we can define these PML layers. So for example, this bottom subdomain here could have extended right to the edges in the X direction, and these subdomains could have been shortened and so on. So, but the important thing I want to emphasize there is that doesn't matter. The end result will be the same, but there is a freedom of choice, of course, in how you can cut off the various parts of the domain that you want. Okay, so for this problem, we will define our grid to be 101 grid points in each dimension. We will define the extent of our domain to be 2 kilometers in each dimension, and we will here use 10 boundary layer points. So now we'll set up the subdomains pictured in this image here. So we'll have our main domain, which is going to be the computational domain, but minus the PMLs. So in the X dimension, we are cutting off the PML layer, and in the Y dimension, we have a free surface on the top, so the computational domain will extend to the top of the Y dimension, but on the bottom of the Y dimension, again, we need to cut off 10 grid points. A left grid point will be defined similarly. Our left domain will be defined similarly, where we're utilizing the entire Y dimension, but cutting off 10 in the X direction, and so forth for the right and base subdomains, which are all then defined using these keywords right, left, and middle. With our subdomains defined, which are cutting off the appropriate parts of our domain, or which span the appropriate parts of our domain, we'll initialize these subdomains. And since you notice when we set up these subdomains, we were using the property self.pmls to pick the number of grid points, which are going to be used for our boundary regions. We need to then pass that to the initialization of the subdomains, so then it is used appropriately. So of course, so this is just illustrating that these objects can be set up with flexible parameters, which you can configure as you wish for sort of easy sort of reusability and flexibility and so on. So now we will set up our grid. So we'll pass the shape, extent, and the forward subdomains we have just initialized above: main domain, left, right, and base. And we will pick out then the grid dimensions. So we'll set X and Y to be equal to the grid dimensions because we're going to need these with the configuration of the PML layers. Okay, so now let's set some parameters for our acoustic model. We'll set the velocity to be equal to 4. And then from thu-devito, we'll import time function, vector, time function, and node. So you see the new object being imported here, which is a vector time function. And this is a time function which then has a time function within each of the grid dimensions. So if we're define a vector time function on a 3D grid, this will essentially be a time function in each dimension. And so this is a convenient interface added in the thu-devito 4.0 to allow the easy specification of vector and tensor mathematics symbolically. So there's also, we're not actually going to use it in this tutorial, but there's also a tensor time function, which maybe I won't go over that in any more detail for now, but if any sort of questions about the vector and tensor time functions, if there are any questions about these, please bring them up on Slack and we can go over them in the Q&A. Okay, so then we just specify our wave field U. Here we'll use a space order of 6. And here, again, something I won't talk about in too much detail, but owing to the mathematics we need for the implementation of this PML, we need to set this staggered property. So now A, which is just an auxiliary function, part of the PML model we're using, is going to be a vector time function. And then we just set this up on our computational grid. So then, similar to what we've done before, for the wave propagator, we set our T0, Tn time step, and hence we can create our time range, which can then be used to construct our Rika source. And then we just choose the coordinates for our source, which we set our domain to be 2 kilometers by 2 kilometers. So here we're just saying that we want our source to be right in the center of the computational domain. And again, source.show will plot the signal in time of our source at the source location. Okay, so these are just some damping parameters which we're going to need in our boundary layers for the PML implementation. So that's all I'll say about those. And then we can set up our equations. So our equation for U in our subdomain is given here. So this is just the stencil we wrote out previously, but now written down explicitly. So instead of using the solve capability, we are simply just writing out what that solve gives us explicitly, and we're passing for this equation. We're passing it the main computational domain. We also need to do something with our auxiliary field in the main domain, which is given by this equation here. So again, the details of this particular mathematics are not sort of important for what I'm trying to get across here. I am again just trying to emphasize that how these components can be combined to form these conditions within the DeVito. So on the left-hand side, we then need to define our wave propagation field, which now has this added component owing to the PML implementation, and then we just pass that our left subdomain. Again, our auxiliary field needs to be updated within this domain, and we can do a similar thing for the right side and the base of the domain, where we're just setting up our equations, setting the adding the appropriate term for the PML implementation to our U equations, and passing the subdomains on which we want this modification to be applied. Again, so then we'll pick out the step-in dimension and set the pressure field to be 0 at the boundary. I think, yeah, and then set up our source term as we did previously. Again, this is the second order acoustic wave equation, so we get this dt squared times velocity squared modification we need to apply to the source term, and then we can form our operator. So then we just pass it all the equations we have set up above along with the source term. and this is then the BCU, the upper Dirichlet pressure condition. Then we can run that operator and look at the plot of the look at the plot of the result. So here we can see that we had a source in the middle. We fired the wave off. Should point out that the main chair is quite small, and we have only a 10 PML layer, so we see some reflections here, but you can see the evidence of the wave being damped appropriately. And then off the top surface, of the free surface condition at the top, we're getting this large reflection. Okay, so that concludes sort of all the main material I wanted to cover in this tutorial. So we will adjourn for 1 or 2 minutes, and then me and Gerard will be, or me, Gerard, and Matt will be back for a quick Q&A session for anything you would like to ask about DeVito.
Okay, we're back. And so I'm going to maybe just relay one of the questions here. Yorgos was asking about some machine learning applications, specifically with seismic data. And Gerard did mention like Lucas Moss's paper, for example, with generating data. But, have you seen other applications in geophysics, especially with machine learning, or even in sort of machine learning beyond geophysics? What's going on in that space?
So, yes, so as you mentioned, Jared has posted a link to a paper in the Slack channel. I personally have not been involved too much in any of those developments. So there are people better placed to post answers with regards to that question in the Slack channel. But I know that there is we are interested in pushing in that direction, and sort of certainly so using DeVito's computational power
Hmm.
to use sort of to design a framework for, say, doing the convolutions which are required in machine learning is sort of something we want to look into.
Yeah, right.
Um,
I mean, and what about these applications beyond geophysics for actually just the DeVito core itself? Even if they're not in machine learning, like you did already point to an example in fluids, but I, I guess it would be interesting to know if you feel like the DeVito team knows about all the applications that are going on, or like how many of those other scientists and developers are talking to you and your team? But the ones you do know about, like how broad is that application sort of space?
so yes, clearly our main focus of applications has been on seismic problems, but DeVito is designed to be a completely general
Hmm.
finite difference, tool for finite difference discretization. So anything which you can solve with a finite difference scheme, DeVito is, or an explicit finite difference scheme, I should say, at this point in time at least. DeVito is, a could potentially be used there. So in our main uh, DeVito repository, we have sub examples of other applications using DeVito. So back on the Jupyter Hub, if you navigate into the DeVito folder and go to examples, so in here, so you can see there's a folder finance where we have a notebook uh, looking at how to solve the Black-Scholes equation with DeVito, which was so a nice contribution from an external contributor recently. And also we have this CFD folder where we have various examples solving CFD problems. We are sort of working on getting explicit methods into DeVito, so that's a work in progress. And so when that goes in, there'll be a range of new tutorials accompanying that. And also we have a PhD student working with the DeVito group who's looking at fluid transport problems for sort of nuclear uh, based problems. So there is interest and ongoing research in other fields.
All right. Yeah.
Yeah,
Just to add in there, it is surprising, like say, and like some of these projects obviously are open and some is closed. So obviously
Sure.
nuclear is closed. There's another PhD student who's doing medical imaging. So I think there's a few people interested in using this with medical imaging. I think it would be just quite exciting as an idea. Um, but then, like, in terms of how people interact with us, of course, some people like are joining in as open source and even making contributions. And amazingly enough, some of those open source contributors are now actually from the oil and gas industry, which, like, they're not guys that have a great track record in contributing to open source. So this is a really nice change to see. But of course, then there's a bunch of other stuff that we don't hear about, and we can get surprises, further down along the line, with some very large PRs where people have been working quietly away with them. So it's nice. I think it's a growing community, and there's more and more application diversity there, which is a lot of fun.
Yeah, it must be really exciting to see the project developing that way. I'd love to know what your team is most sort of excited about, things that you're working on, future releases. Like last time I spoke to you in any, I guess the last couple of times I've spoken to you, the first one that comes to mind was the work you were doing on GPUs and getting DeVito to talk nicely with GPUs. And then last year at the hackathon, the Software Underground hackathon in London, I remember chatting to Navjot about the compression stuff that he was working on. So what's sort of the hot thing right now in DeVito land?
I guess there are a few hot things. I guess one thing which I've been working very actively on recently is our new benchmarking suite, which is where we're using DeVito along with GitHub Actions and the Azure Cloud to automatically generate a whole range of benchmarks. So I can quickly just show that repository. So if we go to on our GitHub page, we go to the DeVito codes repository. Then we have the matrix. And so what it is using GitHub Actions along with various sort of PowerShell scripts to start and stop up virtual machines on the Azure cloud and run a suite of benchmarks. So here we have a list of the machines being tested, and then here are as a list of the benchmarks being run along with links to the results. So if we want an example, look at gigapoints for a 3D elastic run, we can click on that, and there is various information available there. So I should sort of emphasize this is a work in progress, and it's very fresh, and we're in the process of tidying everything up and making it more digestible.
Yeah.
And also so currently we're just using Azure Cloud machines, but we're in the process of setting up benchmarks on some other hardware as well.
Yeah. Are those unladen swallows in that other table? I don't understand that. Logo there.
So this is we're utilizing airspeed velocity, the package airspeed velocity.
Okay.
For anyone who's here, and this is the the symbol.
Yeah,
that's cute.
So I think it's fair to say there's a whole bunch of things going on at the same time. A lot of it is driven. So we have a project going with Microsoft at the moment, and that's sort of driving a lot of our getting everything working on the cloud, making everything cloud native, like doing all this extensive benchmarking as well, having the whole lot automated. Like we're working with down under Geo Solutions as well, obviously. So like DeVito is basically the computational engine behind DugWave. So that's been really interesting in working with industry, because they have a business to run, so stuff has to run and it has to be correct and it has to be fast, and that has been great. And that's a day-to-day make things go faster type effort.
Yeah.
And also then that adds the extra pressure to have high performance on different architectures as well. there is like you mentioned the machine learning. I think immerse boundaries. I think the support for complex geometries I think is important. I think these are things that has to be appreciated, are really complicated to program and get correct. Like the mathematics is difficult and the implementation is really, really hard.
Right.
And I think basically, like, building this into this sort of code generation framework and to implement all of that and get it correct and validated and available on different platforms, I think it's pretty important. And more like, I think the most thing we probably were all excited about is an increasing number of open source contributors. So that's not just us anymore. So
Right.
we have other people that are starting to answer difficult questions for us on our Slack space. That's really, really awesome.
Yeah, that's great. Yeah, I saw there's more than 40 contributors now on your repo there. That's fantastic. And it's, so if a person is, feels like they would like to maybe be involved, but at least stay in touch with the team and keep abreast of all the sort of news, is that an open Slack that they can join, or how should they do that?
So we have an open Slack channel. So I'll just share my screen again here. So if you go to our main project page, thu-devito.project.org, on that we have a range of useful links. And on the right there, you can see the Slack icon.
Oh, sorry. I think I've covered it up with your face. Hang on. There we go. Okay. So the YouTube viewers at home can see that now.
Yeah. So on our main page, we have our little Slack icon. Click on that, and then you can join our Slack. Okay,
that's great. And it's clear that you all have put some real effort into inviting new contributors and giving people learning resources. I mean, like you say, the mathematics here is not something that we're all equipped with. I wouldn't pretend to be myself equipped enough to follow all of it, but that's something that's changing, and we're all getting more literate, more quantitative, more digital, and looking for tools like this. So I think you all seem really well prepared for that kind of, the revolution that we're in right now. So it's really exciting to see. Is there anything, before we wrap up or say goodbye, is there anything you're sort of dying to tell people that you haven't been able to mention yet?
I'm pretty exhausted after talking for 3 hours. But I'm sure Gerard has something to.
I think the only thing I would finish on is, like, I think that we have to just take the opportunity to say massive thanks to all our community. So we have a great team. We have a great team behind it. Between this is born out of Imperial College, and then obviously with a very close collaboration with Felix Herman, UBC and Georgia Tech, along with his postdoc Matthias Lebouton, who has been just a massive external contribution from the get-go, and I don't think he sleeps. He's so, and I think a project like this only comes around just because everyone sort of understands the requirement for productivity, that abstractions are important, that we're trying to create a much broader ecosystem of open source software that must play nicely and be interoperable with all these other tools, and it must be performant. But I think it's fantastic, this whole, not just and this is it reflects on all of the Swan community, this emphasis on developing open source an open source ecosystem to allow us to do a lot more sophisticated and complex science, that's reproducible and very high quality. So I think it's great stuff. I think this is exactly how science is going to move forward quickly.
Absolutely, yeah. Well, thank you very much, Rhodri. Really appreciate the time you've taken and the care you've taken walking us through DeVito there. And thanks as well to the DeVito project for being a reliable and just lovely, friendly supporter of Software Underground and our community events makes a massive difference. So it's been great having you here this morning. I think that's everything. Cheers, guys.
Thank you.
Go on.
I just wanted to say, a big thank you to you and the organising team for arranging this and giving us the chance to.
No, totally. This is what we live for. The conversation will continue, I'm sure, in Slack, in the Slack channel. We'll leave the Slack channels for this week open for at least a little while before we archive them, because there are rather a lot of them. But do jump in there, and don't forget there's several more tutorials coming up later on today, so dive in there, and plus the lightning talks to look forward to, which I'm pretty stoked about as well. So exciting day ahead. Tomorrow as well, but for now we'll say goodbye, and thanks again, Rhodri. Bye everyone.
Thank you.
Fantastic. Everyone.
Bye.